Greetings everybody. In this video we are going to be discussing continuous time density-colored bifurcation diagrams. Okay, so I will be presenting the results from this very recent work called Continuous Time Density-Colored Bifurcation Diagrams in International Journal of Bifurcation and Chaos. I'm going to put a link in the description, and also I'm going to put a link to the code in MATLAB so you can download and run it for yourself. I have a previous video very analytically explaining the classic bifurcation diagrams. Okay, so here we're going to discuss the variation, which is the density color diagram. So let me remind everybody of the bifurcation diagram in case you haven't seen the previous video. Basically, the bifurcation diagram is a diagram that shows us changes in the qualitative behavior of a continuous time system as we change a specific parameter of choice. Okay, and how does it do that? On the x value, we put the different values for the parameter that we want to study for our system. And on the x-axis, for each different parameter value, what we plot is the local maxima for any state of our choice. Okay, so by looking at the diagram, we can immediately understand for the specific parameter value, how many local maxima do we have? We have one local maxima, we have period 1. We have two local maxima, we have period 2. We have more local maxima, we have period n, or we have an innumerable number of local maxima, so we have chaotic behavior. Okay, and the pseudocode for plotting this diagram is very simple. You will easily understand it if you see it in MATLAB or any other programming language. Okay, so we start by choosing a specific bifurcation parameter of choice. Let's say for the Rossler system that I'm using, I'm gonna choose parameter A. So after I choose the parameter of choice, I initialize the values for the other parameters, so B and C or what other parameter I fix them. The initial conditions of the system, x1, 0, x2, 0, x3, 0, I also fix them to a specific value. Then I choose the bifurcation interval that I want to study for this parameter, for alpha, let's say from 0.3 to 0.45. And I choose a very small iteration step that we increase and increment the parameter each time. So then basically to plot the bifurcation diagram, I simply have a simple for loop. I start from the first value 0.3. Okay. I simulate the system for a considerable time. After I obtain the solution, I discard the transient, let's say 500 seconds. And then for the resulting solution, I choose any state of my choice, x1, x2, x3, x4, whatever, doesn't matter. Qualitatively, we will have the same diagram. Let's say I choose the first state of the system. Okay. After I discard the transient, as I said, I find the local maxima for this state of choice, and then I plot vertically the local maxima that I found. So the x-coordinate is the parameter alpha for this value of the for loop, and the y values are all the local maxima for my state. Then I increment the value alpha for a very small value, and then I redo the system again. I solve the system again, I discard the transient, I find the local maxima for my chosen state, and I plot the local maxima on the x value of alpha. Then I increase the value of alpha again, solve the system, discard the transient, plot the local maxima, okay, and then increase the value again and again and again until I finish my for loop. Okay, so the code is basically very easy. Remember, in most programming languages, to find the local maxima, you have built-in functions. So don't worry about finding them. It's very easy. You can do it with a simple command. So the graph that we are going to get, here I'm using the Rossler chaotic system, a very well-known system, is something like that that immediately tells us how many local maxima we have for each parameter value in the x-axis. And from the amount of local maxima, we can immediately understand the type of behavior. So for the smaller values of alpha, we have, for example, for 0.3, one local maxima, which means period 1. In the intermediate values from 0.34 to 0.36, 37, we have two local maxima because we see 2 points. Remember, you need to look at this graph for each value vertically. So each time you see how many values you have in a specific vertical line. Okay. So in this range we have period 2 because we have two local maxima. Then for a smaller region right here 0.37 and so on, you have 1, 2, 3, 4 local maxima, so you have period 4. And for all the other values that are very dense, the black regions, as we can say, here we have an innumerable number of local maxima. Basically, we cannot count how many local maxima we have, which is of course indicative of chaotic behavior. See here, for example, for 0.45, I hope I'm not blocking the view, you can see very clearly that we have chaotic behavior. And for all the dense regions right here, we have chaos. So what is a density-colored bifurcation diagram? This is the variation that we propose in our own paper. The density-colored bifurcation diagram is a variation built on the actual bifurcation diagram, which does what? It colors the bifurcation diagram based, on the density of the local maxima in the state space. And what do I mean by that? We find all of the local maxima for a specific solution of the system, for a specific parameter value. And for this local maxima, we basically take their histogram. The histogram tells us in the state space how many local maxima we have in each bin. How many bins you can decide for yourself. And based on how many maxima we have in each specific bin, we then go and plot the bifurcation diagram with color, and give different colors based, on the frequency of the local maxima in each region. When I say bin, you can understand. Let's say bin refers to a specific region in the state space. And we obtain a diagram like that. So why is this useful? Well, for the periodic regions, it is not useful because periodicity is not chaos. So we're not interested in the statistics of periodicity. They're very easy to derive. But for chaotic regions, we can immediately understand how many local maxima are more common in subregions of the graph. So immediately we can understand some information about the statistical behavior of the time series. So let me give you an example. So here, for example, I have another diagram for which I have computed also histograms. This is again for the Rossler chaotic system, but the previous diagram was with respect to A, this is with respect to B, and this is a bit more interesting, so let's focus on that. So you see the diagram, the bifurcation diagram on the left, and here you see the bifurcation diagram with density color on the right. So what we can observe from this diagram? We can observe some regions, see for example the color yellow indicates a higher density of local maxima, which tells us, as you can see, we have a very clearly, in the chaotic regions, a very clear non-uniform color, right? Some regions are blue, which have lower density, and some regions are green-yellow, which have higher density. This tells us that the amount of local maxima for the time series, the x1, is not uniform across the state space. So for example, for beta equals to 0.2, see this vertical line right here, you see that we have some specific lines right here that indicate that on this lower part of the graph, I have a higher density of local maxima. Then on this part of the graph, I have a higher density of local maxima if you follow my mouse. In this region in between, we almost have no local maxima. And then on the highest part, which is also again very, very yellow, we again have higher density of local maxima. So indeed, if I plot the time series solution of the system and take the histogram of the local maxima, which I have plotted as you see in this graph right here, this is what we observe. Exactly what I told you. We have a higher value of local maxima on the left right here, which is close to the value of 4. Indeed, here we have a much higher yellow value. In between, we almost have no local maxima, which is right here. Then we have this small line which indicates local maxima, again, around 7. And then on the higher part of the graph, which is around 11, we indeed have a very high value of local maxima, right? And we can derive such information from any other part of the graph. See here, for example, for the value around 0.6, let me remove the graphs. You see that we have yellow right here below around 5, and then we have a light blue region which indicates lower density, and then on the highest part of the graph we also have a higher yellow region which indicates a higher density of local maxima. So again, if I show you the graph, you see that on the left we have a higher density of peaks, and then on the right, on the left part of the graph, we have again a higher density of peaks. This tells us that time series solution in both cases is non-uniform and that local maxima appear on specific sub-regions of the state space. Okay, so this is very, very nice information about the statistical behavior of the local maxima and basically the statistical behavior of the time series solution of the system. So it's very interesting information if you want to quantify if the system has uniform distribution, okay, if the system has some regions, especially if it is a bit biological or another system with a physical interpretation, if it has some values that are more common, okay. For a physical interpretation, this is very interesting. I think I have another diagram right here. Again, for the Rossler system, the parameter of study here is se. And again, you can see, of course, they look the same, but on the bifurcation diagram with density, we have a color. And you see that there are specific regions that have higher densities of local maxima, while there are other regions with lower densities of local maxima, as indicated by the color bar right here. You see yellow is higher density, blue, dark blue is lower density. Okay. So for example, here, let's say for say equals 35, which is the end value, you see four specific, very small subregions, right here, right here, right here, and right here with peaks. This will tell you that the histogram for this value, for the local maxima, will probably have four distinct peaks. And since this region is a bit more yellow, probably it's going to be a bit more right skewed. Okay. And the same holds for the other values. For 15 and 20, pretty much it's going to be a bit more right skewed. And indeed, from the graphs, we can verify this. So for example, for C equals 35, we see the histogram right here. And as I told you, we have 1, 2, 3, 4 distinct peaks right here, right here, right here, and right here. And it's slightly more skewed to the right. And for the other solution that I have also the histogram of the local maxima, we have this C equals 20. And again, we can see 1, 2, 3, 4 very clear yellow lines for this range. And also the highest part of the histogram is a bit more likely towards the yellow color, which means that this sub-region right here is going to have the highest density of peaks compared to this region, which has a lower density of peaks. So indeed, the histogram of the local maxima verifies that. Okay, so the idea here is to color the bifurcation diagram in order to extract some information about the distribution and the statistical behavior of the underlying time series solution. Okay, this is going to be useful for applications. For example, in chaotic encryption, this is very important. In chaotic path planning, this is very important because uniformity will affect the behavior of algorithms in data security or in chaotic path planning. So it's very important to derive that. But apart from applications, in a chaotic system that has a physical meaning, it's very important to understand if it's some sort of physical system that has some underlying interpretation. It is important to understand how the system behaves in any case with respect to its statistical properties. And of course, from a mathematical perspective, again, it is very, very interesting to be able to study something like that. Now, this is the graphs that I wanted to show you. I will put a link into the description for the paper in case you want to read it. We have a very, very extensive analysis because we have many more diagrams and we also have diagram variations based on how we use the histogram to compute the maxima. I'm not going to give details in this video. I don't want to make it very long. I'm also going to put a link into the MATLAB code so you can download and plot the diagram for yourself. Any questions that you have, write them down below, but I strongly suggest you also read the paper. Don't just go straight for the code. Okay, but any questions, write them down in the comment. So thank you very much.